So last lecture, we defined the notion of an algebra and sigma algebra on a set. And now let's go over some basic properties of these two notions. So first of all, let's let A to be an algebra, and let's use B to denote a sigma algebra. Then the first property I would like to mention is that, first of all, an algebra, if you have two sets, we know the algebra is closed undertaking their union. But in fact, algebra is also close undertaking their intersection, and also is close undertaking their set difference. So here the E take away F, so if you have E here and you have F here, the E take away F corresponds to the thing that's in E and it's not in F. Well, this is fairly simple to see. Well, here's the proof. So first of all, to show that E intersect F is in the sigma algebra, then what we can do is that we consider its complement. Well, the complement of the intersection is the union of the complement. So this is the union of, let's write it this way. This is the complement of E, union complement of F. So now, because A is an algebra, what we know is that the complement of E is inside the algebra, because A is closed undertaking complement, and also the complement of F. And now, because A is an algebra, is closed undertaking finite union, so the union of these two complements is again an element in A. So this is in A. So now we know the complement of E intersect F is an element in A, but again, A is closed undertaking complement. So we take the complement of the complement, we'll recover the E intersect F. So this is basically the complement of the complement. We know is in A as well. And to see that E take away F, this set is in A, well, we just need to notice the following. So what exactly is the E take away F? Well, we can write it as the intersection of E and whatever that's not in F, so that's the complement of F. And we just show that the intersection, well, the algebra is closed under this intersection, and the complement of F is in A, so this intersection again is in A. So this shows the set difference. E take away F is in A. And of course, because A is an algebra, you can also, that's an easy exercise, you can do the induction on this intersection. So if you have a finite intersection, then you know is also inside the algebra because A is closed under finite union, and you do the same trick, or you just apply the intersection of two sets inductively, and eventually you get K of them. So we know for algebra is closed under finite union and set difference. And similar thing you can show for sigma algebra. So if you have a bunch of sets, a sequence of sets, so here n going from 1 to infinity, that's in B, then their countable intersection is also in B. The proof should be really the same. So if you want to show the intersection is in B, you consider its complement. And this intersection, the complement of the intersection is the union of their complements. And it's easy to show that this is an element in B because each of the En is in B, so their complement is in B. All right, so these are some two basic properties, and there's one more thing I'd like to show about the relation between an algebra and a sigma algebra. So it uses a nice little trick. We will be using this trick eventually, so I'll do a proposition right here. So let's recall the difference between an algebra and the sigma algebra is that the sigma algebra is closed under taking countable union of any collection of sets. So how about we only require taking countable union of disjoint sets? And I want to show that it gives you the same thing as a sigma algebra. So here's the proposition. So let's let A be an algebra. And suppose that we know that A is closed under taking disjoint union. So what do I mean by that? Is that for every an, let's say n going from 1 to infinity, and if they're disjoint, then their union n going from 1 to infinity of this an is in A. Suppose I know that this algebra satisfies this a weaker condition compared to the sigma union. It's only a countable union of disjoint sets here. But I want to show that this is enough for A to be a sigma algebra. So the conclusion is A is a sigma algebra. So basically, only requiring the countable disjoint union is enough for A to be a sigma algebra. So what's the idea of this proof? Well, it uses a little trick of breaking this union into disjoint union, and I'll describe this trick here. You may have seen it if you've taken PMATH 450. It's a trick that we'll eventually use in later proofs. So let's start. So to show that A is a sigma algebra, because A is already an algebra, we just need to show A is closed under taking countable union. So let's let a collection of sets n going from 1 to infinity of En. That's a collection of sets in A. So the goal is to show that this union, this potentially non-disjoint sets, that's in A. And to show that's in A, we have to use this property. So this property here. So the idea is we want to write it as a disjoint union of some sets An, where An are disjoint, and they're in A. So that's the idea. Okay, so say here's the idea. All right, so how do we do this? Well, let's just consider them one by one. So let's consider these sets. Well, E1, well, I want to write it as a disjoint union. Well, E1 is the first one. I might as well just take everything for A1. So let's just let A1 to be E1. So let's draw a picture here. So I have E1, and I just say that's just A1. And now let's consider what happens when we have E2. So E2 may have some intersection with E1, but as you can see, we can just consider their set difference, this part. So suppose I let A2 to be the set difference. So I let A2 to be whatever that's in E2, but I take away the things in E1. Well, then I get A2 is disjoint from E1 because A2 doesn't have anything from E1, so they're disjoint. And now let's continue. So let's do another one. Suppose now I have E3. So this is E3. So if I want to make something that's disjoint from both E1 and E2, then what can I do? Well, I need to take E1 out, and I also need to take E2 out. So I need to end up with this region. So that's everything that's in E3, but it's not in E1, and it's also not in E2. So it's not in the union of E1 and E2. And now you can kind of see the pattern here. So if you just keep going, you can write down some formula. So for the En, if you want to find something that's disjoint, so you better let An to contain everything in En. but you don't want anything from the first n minus 1 of them, so you take away the union of I going from 1 to n minus 1 of these ei. You don't want any of them. So now we can just keep going, and we get a sequence of an. They look quite disjoint to me, and hopefully this union of en is equals to this union of an. So let's try to prove this. So here's the claim. Well, the first claim I want to make is that the union, if I just take the first, say, k of them, of these an, then I get the first k of the ens. Well, this is an easy exercise if you do induction, so I'll just leave it as an exercise. It's an easy exercise using induction. And as you can see, is just from the picture, if you just do A1, that's equals to E1. And then starting from A2, A1 union A2, then it contains everything that's in E2 or in E1, so I get E1 union E2 and so on. So that's quite easy. And the second claim I want to make is that these an are disjoint. Well, why are they disjoint? Well, you can see the following. Because the way we define these an, the an is intersection with the union of the first n minus 1 of these ei's. Well, that's going to be an empty set. Well, because an literally just takes away anything in that union. But we show that from the first claim, this union is basically the same if you use ans. So that's the same. So these two are the same. So this intersection is also empty. So an is disjoint from the union of the first n minus 1 of these ai's. So ai and an are disjoint, and you can just keep going. You can show an are disjoint. And thirdly, these an are really inside your algebra. And why is that? Well, by our definition, this an, by definition, that's equals to en take away the union of the first n minus 1 of these ei. Because A is an algebra, we know that the finite union is in A. And we just showed one of the basic property is that if you take two elements from an algebra, then their set difference is also in the algebra. So an is in A. So now we have a collection of disjoint sets. And by the way, using the first condition here, we can easily replace this k by infinity. Just take k goes to infinity. So now we have that the union of n going from 1 to infinity of these en, that's also the union of n going from 1 to infinity of the an, and an are disjoint, and we know by the assumption that this algebra is closed under taking disjoint unions, then this one is in A. So this is by the assumption. So we show that A is now closed under taking countable union. So A is an sigma algebra. So A is sigma algebra. All right, so we show that basically if I replace the definition of a sigma algebra where I require countable union, I replace it by countable disjoint union, then we get the same thing. We still get sigma algebra.